Myself Nagarajan, Assistant Professor in EC Department, Rohini College of Engineering and Technologies. In this video, we see about the biomedical engineering subject, embedded system and IOMT. The topic is here interrupt controllers. So in this interrupt controllers, we, we want to define what is interrupt controllers and what is the need for a interrupt controllers in the embedded product. Okay, let us see the definition of a interrupt controller. So interrupt controller is a hardware module that manages interrupt signals from various peripherals and direct them to the central processing unit. So it prioritizes interrupts, handles multiple interrupt sources and ensures that critical events are promptly addressed by the processor. So interrupt controllers are essential in embedded system to manage asynchronous events, ensuring that the system can respond quickly to real-time requirements while maintaining efficient operation. So let us see the type of a interrupt. The first type is a hardware interrupt. So generated by external hardware devices such as a timers or input-output peripherals, sensors or communication interfaces are called as a hardware interrupt. So hardware interrupt means it is generated by a external hardware devices. So hardware interrupt signal the CPUs to stop its current task and execute an interrupt service routine to address the event. The next one is a software interrupt. So software interrupt is triggered by software instruction within the processor. So software interrupt, these interrupts are used to perform context switches, system calls, or to handle specific software defined events. And next one is a maskable interrupt. So this type of interrupt that can be disabled or masked by the software to prevent them from being processed by the CPU. So maskable interrupts are commonly used in scenarios where the system needs to complete a critical task without being interrupted. The next one is a non-maskable interrupted NMI. So high priority interrupt that cannot be disabled by software NMI are used to emergency tasks such as responding to hardware failures, system errors or critical power management events. Now let us see the function of a interrupt controllers. So interrupt prioritization. So interrupt controller priorities incoming interrupts based on their importance and urgency. So higher priority interrupts are served before lower priority ones, ensuring that critical tasks are handled promptly. Next function is a interrupt vectoring. So interrupt controllers provide the address of the appropriate interrupt service routine to the CPU when an interrupt occurs. This process is known as a interrupt vectoring, which allows the CPU to jump directly to the correct ISR without additional processing. Next function is a interrupt masking and unmasking. So interrupt controllers allows specific interrupt to be masked, or that is a disabled, or unmasked, that means is a enabled, depending on the system current state. So this flexibility is important in controlling the flow of interrupt processing and preventing unwanted interruption during critical operation. The next function is a interrupt nesting. So interrupt nesting, some interrupt controllers support interrupt nesting where a higher priority interrupt can interrupt the processing of lower priority interrupt. This feature is useful in real-time system where certain events must be handled immediately regardless of the current task. Now let us see the architecture of a interrupt controllers. So first one is a programmable interrupt controller, that is a PIC. So programmable interrupt controller is a traditional interrupt controller used in many controller architecture. It allows the programmer to configure the priority level of the interrupt and manage the interrupt request line. And programmable interrupt controllers is typically support cascading, allowing multiple PIC to be connected to handle a large number of interrupts. The next one is a advanced programmable interrupt controller, that is a APIC. So APICs are used in modern microprocessors to support a large number of interrupts and more complex interrupt handling. They are commonly used in multiprocessor system and support features like interrupt routing, interrupt balancing, and more granular interrupt prioritization. The next one is a interrupt controller in ARM Cortex M processor. The nested vector interrupt controller is an integral part of a ARM Cortex M processor, providing low latency interrupt handling, support for interrupt preemption, and configurable priority levels. The NVIC directly interfaces with the CPU core to manage and service interrupt effectively. The next one is a dedicated peripheral interrupt controllers. Some peripherals include their own dedicated interrupt controllers to manage interrupts specific to that devices. This approach reduces the load on the main interrupt controller and allows for specialized handling of the peripheral specific event. Now let us see the application of a interrupt controllers in a embedded system. So first application is a real-time embedded system. Interrupt controls are vital in real-time systems via timely response to events in critical such as the automatic control systems, industrial automation, and robotics. Next application is a multitasking operating system. In embedded operating system, interrupt controller facilitate multitasking by allowing the CPU to switch between tasks based on interrupt. This capability is essential for maintaining system responsiveness and ensuring that high priority tasks are completed on time. The next one is a communication system. Interrupt controller manage data transfer and communication even in system with high data throughput such as network routers, wireless communication devices, and IoT gateways. The next one is a power management. Interrupt controllers play a role in power management by handling interrupts related to power saving modes, wake up events, and battery monitoring. Now, in the interrupt controllers, what are the challenges we faced in a interrupt controllers? First one is a interrupt latency. So the time it takes for the CPU to respond to an interrupt, it is a critical factor in real-time system. Minimizing interrupt latency is essential to ensure the high priority tasks are not delayed. Next one is a interrupt storms. Interrupt storms occurs when the system is overwhelmed by too many interrupts in a short period, so leading to system instability or crashes. The next one is a debugging interrupt driven subsystem. So debugging systems with complex interrupt handling can be challenging due to the asynchronous nature of interrupt. Developers need to carefully design ISR and use debugging tools to trace the resolve issues. The next one is a balancing interrupt load. So multiprocessor system distributing the interrupt load evenly across CPU. Now let us see the importance in embedded system while using a interrupt controller. So first one is a enhancing system responsiveness. So interrupt controllers are crucial for maintaining the responsiveness of embedded system, allowing them to quickly react to external events and process tasks in real time. The next one is a efficient resource management. By managing multiple interrupt sources and prioritizing them approximately, interrupt controller help optimize CPU utilization. And next one is a supporting real-time operation. In real-time application, where timing and deterministic behavior is essential, so interrupt controller ensure that the system meets its deadlines. So I hope that all of you understood about the interrupt controllers. Thank you.